Hello and welcome to today's Maniac Talk. To introduce our friend here, I wanted to tell you a short story, not the animal one. I'm going to use a different theme today. When I was growing up as a child, the aircraft were big. It was a big deal, and that was late 60s, early 70s. And whenever we would hear airplanes moving, all the kids would go out and start singing songs and sending messages to the pilots and telling them, wherever you are going to God, tell God that I'm hungry, so I need food. And this was a song that was always repeated, and it became actually a metaphor for parents and neighbors and teachers. Whenever they wanted you to work hard, they were telling you, work hard one day to become a pilot, So that was a major theme. So, but, going back now several decades before me, all the way across the Indian Ocean, a young boy was growing up in the Philippines. And the same story happened. The jet contrails was exciting him, was inspiring him to do greater things. Now today, he is here actually to trace that journey back from Philippines all the way to the United States and make major contribution in sea ice. Please help me welcome our speaker, Josefino Comiso.
Hello, good morning. Thanks, Charles, for the very nice introduction. And thanks also for the opportunity to be part of this Maniac Talk series. When I joined Goddard, I was asked to see Dr. Bonbon, who was then Associate Administrator, I think, for the Earth Science Directorate at that time. And the first question he would ask me is, why would a person like you, who came from the tropics, be interested in studying sea ice and the polar regions? So I told him about the connection of sea ice with the climate system and the fact that the polar regions are actually the ends of the world and the heat sink. And I didn't know at the time that he's actually a joker. He has been going to the Arctic, and one time he was on board a plane with some biologists, and the biologist was taking notes earnestly, looking at the window. So he asked this biologist what she was doing, and she said, I'm looking at the distribution of feces of animals in the Arctic. And Dr. Bonbon said, why would you be wasting your time looking at shit? And the biologist answered promptly, sir, it might be shit to you, but it's bread and butter to me. So, going back to the original question, this is the tropics, western part of the tropics, and you can see the Philippines here. And what you see here is northern Luzon. That's where I was born and raised up. And this is not a very good reproduction, but this is the house where I grew up. I was the seventh of 10 children. We actually all went to college, although my parents did not have a good education. So I didn't have a good science role model. The country is actually converted to almost 90% Roman Catholic because we were underspent for more than 3 centuries. But my parents were one of the few who were also converted to Protestantism by American missionaries. So I was very active with the Methodist Church, very active with the MYF, the choir, and even taught at the Bible schools. And that was me at that time. But then there were events that made me rethink my beliefs. One time, there was a line in the sky seen by the neighborhood, and everybody gathered to find out what that is. The elders then say, it must be a sign from God. And they start saying it's the end of the world. So everybody gathered, and many people were kneeling, then asking God for forgiveness and everything. And I was there, not knowing what to do, because you know, as a young child, it's very hard to say, to know what end of the world really means. You know, does it mean that all of a sudden the whole world will blast off or whatever? But then when we found out that it's actually the contrail of the first process of commercial plan in the area, then that opened my awareness about science. I decided to read more about science and studied biographies of famous scientists like Albert Einstein, Madame Curie, Enrico Fermi, and the like. And then another event happened in the fact that I was still active with the Methodist Church. There was an international workshop that was held in a neighboring province. And we were here in Narbacan. There were 8 of us. The only transportation we could get is a jeep that can fit 6 people. But we decided to all fit in anyway, thinking that it's just 30 kilometers away and we should be all right. But the road turned out to be a very winding road. And in some places like this, the driver was not able to negotiate it properly. And the jeep turned turtle. I broke my femur and then was rushed to the hospital. So the doctor actually did a good job. He put my bones together, put me in a plaster cast, took an x-ray, and then told me that, see, the bones are together. I'll send you home, and in a couple of months, I want you to come back, thinking that after a few months, I'll start to get well and recover. But in the meantime, my brother then has finished medicine. He was taking a postdoc here at the University of Pennsylvania. So I wanted a second opinion. I sent the x-ray to him, and he responded right away that we should take another x-ray, not just from the top, but also from the side. And we did that, and we found out that the bones were still far apart. So what was supposed to be a simple fracture turned out to be very complicated. And I would spend 6 months at the hospital in the plaster cast, looking at the ceiling 24 hours a day. And it was a miserable moment of my life. But then I was visited by a reporter from one of our local magazines. And he said that there are times in life when you slip and fall while climbing a ladder. But when you climb a ladder again, you'll be a lot more careful and will be able to reach heights you'll never dream of ever reaching. So I thought that was a very profound statement, and I kept his word and remembered it for the rest of my life. And then went to the university. It's actually the best university. I was glad I still had my scholarship when I went there. But then with a pair of crutches, it took 2 years before I could get rid of my crutches. But then I didn't know what to major. So I went to a counseling center and they asked me to take aptitude tests. And I was told that I could excel in physics and math. And I chose physics. And I thought I chose the right field because in the end, I was given an award by the president, Carlos Romulo. And actually, I felt that was a great honor because Carlos Romulo was a big figure, a big personality in the Philippines. He came back when General Douglas MacArthur returned to fulfill his promise, I shall return. They were together, and he became Secretary General of the United Nations as well. So when you finished college, it's very hard to get a job. But I was lucky to be offered right away to be one of the first junior scientists hired at then newly opened Nuclear Reactor Center in Manila. And it was my first experience to do scientific research. So I was doing neutron diffraction research with Dr. Navarro, who was actually a fresh PhD from UC Berkeley in nuclear physics and engineering. The work looked very interesting. We had all our instruments ready, but the reactor was low to produce the nuclear beam that we wanted. And in the meantime, I was asked by the University of the Philippines if I would be willing to go back and become an instructor to teach physics. So that was a big attraction. I decided to accept it and I enjoyed the interaction with students. But then I felt myself ill-prepared to inspire the students and to do original research. So I decided to apply for graduate school. And I was lucky to be admitted to Florida State University, where I did my master's degree. After my coursework, I needed to do a research project, and I studied K minus plus P events in a bubble chamber under the supervision of John Albright, who wrote a textbook actually with our famous Paul Dirac, who did a lot of work on spin and electron-positron interactions. This is an example of a bubble chamber image produced. Who are not familiar, there are a lot of tracks here. The liquid is superheated, so if you have a particle going through, you get little bubbles along the track, and you can see particles then. But it's not easy to interpret what's going on. Actually, the most important process that went on at the time is this particular process here. You can see per production over here. If you have a gamma particle decaying into two particles, you conserve energy and momentum, and you can produce per productions. The actual interactions actually is, and it's actually this image that led to the discovery of the mega meson, which was then very popular. After my master's, I decided to try something else. I got accepted at UCLA, but then joined a group that does work at the Lawrence Radiation Lab at Berkeley. And I wanted to pursue particle physics. And I was lucky to be involved with an experiment on time reversal invariance. Time reversal is one of the three fundamental symmetries of nature as predicted by the quantum field theory. They call it CPT. One is charge conjugation, C, parity, P, and T time reversal. And they have already discovered violations for C and P. Young and Lee won the Nobel Prize for the discovery of P, and University of Chicago people won the Nobel Prize for the discovery of charge conjugations. So I thought I was very lucky to be involved with this experiment because that could give us a chance to be famous as well. We had a beam particle here, collimated, incident, and a proton. And then we have two detectors, one detecting gamma particle, the other neutron particle. It's called photoproduction, and we did it at several energies around this resonance particle. To make things short, we analyzed 1 million events, which was very difficult to analyze. Took me 6 months only to digitize the images, because at that time we didn't have digital cameras, and you have to shoot it by film, and then you have to digitize the film after that. And to make it worse, when we come up with the results, we didn't get any violation. So I didn't get the chance to be part of a famous experiment. My only consolation is the fact that I met my wife in the region. We then have 3 kids, and now we have 7 grandkids. So I had to move on. I found a job at the University of Virginia. And actually at the time, there's a new facility in Los Alamos. It's called Los Alamos Meson Physics Facility, where they have unusually high beam of pions. And physicists were thinking then that there'll be a lot of new physics that will be discovered in the area. There's also another facility owned by NASA at Langley. It's called Space Radiation Laboratory, FX Laboratory. Is a synchrocyclotron. And when we don't go to Los Alamos, we go to Israel to do experiments. And we managed to do some of these experiments. It was nice to be working at some of the top institutions in the world. The Los Alamos was the birth, the location of the development of the first atomic bomb, and then we have NASA, which is then very highly visible because of the manned mission to the moon. So the experience made me think about NASA a lot, and I was exploring the possibility of joining NASA. I then have some friends who joined the Computer Science Corporation and who are also involved with NASA work. So I asked them, how to get involved with NASA. And they told me at the time that you can get involved through as a contractor by applying to some of these companies that do contract work with NASA. So I applied and got accepted, and actually started working on aircraft data. It's infrared data with the purpose of validating algorithms for SST. And it turned out to be a good experience because later on I'll be looking at surface temperature in the polar regions. But the work was done after a few months. And at the time I was lucky that Dr. Jay Swally was looking for somebody to work with him on the analysis of Nimbus 5 ESMER data, and with the purpose of creating a sea ice data set. I looked at the pictures. I was really impressed because that was the very first time that I would see satellite images of the polar regions and images of sea ice. So I started working with him, and before I know it, he was asking me whether I would be interested in joining NASA as a civil servant. I guess he must have liked what I was doing. It would take almost a year before I could get in, but we continued the work anyway. There were a lot of data problems. The fact that there was a bit in the ESMER data set that detects whether the data belongs to the northern hemisphere and the southern hemisphere, or the southern hemisphere. And the bit was erratic. So there are data in the northern hemisphere that would be wrongly located in the southern hemisphere. And when you're looking at Antarctic sea ice, you'll see some features that doesn't look realistic. And because we could not predict whether the bit is erratic or not, then it was very difficult to do it by software. We had to do it manually. So it was a laborious process, but we managed to produce a data set and come up with an atlas. And that involved work with Claire and Frank and Per and Campbell. It was actually a project that was well worth it. It was also internationally recognized, and in fact, first time I encountered the Russians, they were telling me that they translated this book into Russians. So I don't know how they managed to copy the color images, which was tremendous in the book as well. We also did atlas work for the Arctic. Claire did the lead work for that, and then one for both hemisphere using simmer and paired to the lead on that. But then I started asking myself, what do I do next? And why am I doing polar research? And actually, there are lots of potential in the fact that the global warming signal is supposed to be amplified in the polar regions, and that's associated with ice albedo feedback. And what you see here is an anomaly for the data 2008 to 2012. The climatology, which is from 1850 to 2012, has been subtracted. And you can see for sure that there's a lot of warming going on in the Arctic region. I've also been analyzing ABSR data, and this is the trend that you get from ABSR data. So if you're looking for signals, it's really in the Arctic region. Now, to do work, you need some funding, and we've been lucky at the time to have Dr. Bob Thomas to be the program manager for polar research. And one time he sent me a Christmas card saying that he's actually providing the Cryosphere people with the most funding, RTOP funding at Goddard. So that was very good. Now, to do research in the polar regions, you have to have background, what the polar explorer did, find some role models and some mentors. I was very new with CIS research then, and I encountered the works of Nansen and read the explorations of Shackleton, Amundsen, and Scott, and then dealt with some of the experts in sea ice and ice-ocean interaction. And then Bill Kemba was also doing a lot of remote sensing work. I was really amazed that Nansen managed to freeze a ship in the Arctic and let it drip for about 2 years just to be able to understand the oceanography of the Arctic and at the same time the atmospheric and sea ice distribution. Of course, we had a lot of mentors at Goddard. This is the group. You can see there Jay, Dan, Per, Nancy, Frank, Carsey, and that's Claire, and Dorothy, that's Bob Bin-Shadler, Jim Puster, and this is Stan Wilson, who is happened to be Bob Thomas' boss, and he was actually very sympathetic with polar research. So my topic includes anomalies in sea ice, and one of the biggest anomalies that we observed from satellite data is actually the large Wadalpulinas. They persisted over the whole winter. It happened in 1973, 74, and 76. It was mentioned by Claire in his talk. People had done a lot of modeling on the Pulinas, and the Pulinas would form, but it wouldn't stay there for the whole winter. So there must be a big oceanographic effect, and in fact the oceanographers made measurement before and after, and they found out the temperature of the water up to depths of 2,500 decreased by 1 degree centigrade. And the most visible proponent of the Wadalpulina was actually Arnold Gordon, because of his background in oceanography in the Arctic region. So together we combined oceanographic data and satellite data and come out with a paper published in Scientific American. explaining some of the basis for the polynya formation. One of them actually is the fact that there could be an upwelling of warm water because of the presence of a rise underneath the polynya where it was formed, causing the polynya to form over here. And it was felt that the polynya is actually a big oceanographic feature. We managed to convince the Germans to have some expeditions with us to the Antarctic, and cruises were planned for 86, 89, and 92. There was also an arrangement with NSF to do a rapid response just in case the polynya formed. This was the first cruise, and as you see here, the track of the cruise went down south into the Weddell Sea. It curved down to the Mount Rice, and then come back here. This is a resupply place for the Germans, and then we visited Mount Rice 2 times just to better understand the oceanography of the region. This is Dr. Ernst Augstein, who was then the director of meteorology at the Alfred Wegener Institute, and he was also the chief scientist. So the day before we reached the ice edge, he was asking me whether I could tell him where the ice edge is located. So I looked at the satellite maps, indicated that we'll reach it at around this point. And so the following morning when we got there, he was looking for me, asking me where the ice edge is. They didn't find the same type of ice edge they would see in the Arctic region, because normally in the Arctic there's a strong contrast between the open ocean and the ice area. But when we look more carefully at the surface, we saw a lot of small pancake ice. They're transparent because they're small and thin, and they just went with the waves, so it was very difficult to identify them. And as we went inside the ice pack, the pancakes becomes bigger and bigger because they are joined together until the point where you can really see the white stuff. One of the reasons why I was involved in that experiment is because I was then developing an algorithm for sea ice, called Bootstrap Algorithm. It was actually a simple algorithm that makes use of 2 channels that enables you to identify the brightness temperature of consolidated ice as well as 100% open water. And to get ice concentration, we normally use a mixing algorithm that looks like that. So in addition to the satellite data, the only unknown is the brightness temperature of the ocean and that of consolidated ice. And the problem is that this changes from one location to another. So you have to be able to adjust. And it turned out that with this scheme, the adjustment is along this line. And this, you can then just construct an algorithm that enables you to get the tie point given any point in this graph. So I brought with me a set of radiometer that has the same set of frequency as what's in the satellite, except the fact that it's only one polarization at the time, so you have to turn it around by 90 degrees to get the other polarization. So that's the setup. We have the radiometer here looking at the surface. We have an infrared radiometer as well, looking, measuring the temperature. And this is the ship as observed from space. And sometimes we'd go around and get to interact with native inhabitants in the region. So these are examples of the data we get in the ship. And every time we hit a lead, you get a feature that leads that looks like this. And all the channels will go down because open water has lower emissivity than ice. But the 89 gigahertz channel, which has very short wavelength, could help us detect the presence of thin ice or grease ice in the fact that it would go up when we cross a lid that has already frozen surface. Another thing that happened is that while attending some of this Waddell workshop that came out of those cruises, I met Dr. Neil Sullivan, who was at the same time organizing a cruise in the Arctic. It's called an Arctic Marine Ecosystem in the Marginal Ice Zone. There's a lot of interaction between ocean and ice, and he told me that we'd be interested in having a better coverage of sea ice that they can study to see if they can find a relationship of the sea ice cover with the blooms that are going on there. The theory is that when the ice melts, you introduce meltwater that's relatively fresh, so it's less dense than seawater, so it floats. And because it's on the surface and it's stable, can have abundant sunshine, it's an ideal platform for photosynthesis, and that's the reason why you can have blooms. And I look at the data and see these blooms right at the ice edge itself. So I was convinced that it's a nice theory. We were able to make several studies on this, some published in the Science and JGR. Another anomaly that you observe from sea ice is the ice tongue. It's called the Odin. In the Greenland Sea, all of a sudden, you see a tongue that looks like that. But the most important feature here is actually the embedment. Here it's called Nurbukta. And this embedment is actually where most of the ice is formed. They're then advected to the Odin area. And it's the location of one of only 4 regions in the world where they have deep ocean convection. We published a paper in 2001 that ends analysis of data in 1999. At that time, the Odin was very active. It was actually very, very active in 1997. But since that paper was published, then the Odin started to disappear. And in recent years, you don't see it at all. So we are thinking that that might be also a consequence of the changing climate in the region. Another thing that we did, that was actually a collaboration with Dr. Peter Wadhams and his wife, Pia. As you see, Pia has a gun and Peter has a spear. They're using that as a protection from polar bear attack. I also had a collaboration with Peter to look at the thickness of sea ice and also get a better handle about the passive microwave signature of different ice type. So this is the group. This includes Dr. Eric Molos Christensen, became chief of the Ocean Laboratory. As you see, Nancy is there, and Dave Clem is here. Nancy was branch head, Dave Clem is branch head at Wallops. And some other familiar faces here, that's John Crawford, Bill Krybel, and Bob Swips, who have been very involved with altimeter studies. So the scheme was to overfly sea ice simultaneously by the submarine and the plan. We're supposed to be on top of each other. So we can measure the same portion of the sea ice simultaneously. And during that time in the Cold War, when it was very difficult to establish logistics, we managed to get some segments where we were actually coincident. And we're able to establish that we try to get the thickness distribution from the air using laser, you get almost identical distribution from the bottom using upward-looking sonar. And that kind of results was actually applied later, because later on we launched ISAT-2, ISAT, and subsequently there's also Cryosat, looking at the thickness of the freeboard. And with ISAT, it has been able to establish that the thickness of the ice has been quite lower than that previously as measured from submarine by maybe as much as 1 meter. Another anomalous event that was happening in the Arctic is the perennial ice. The perennial ice is ice that survived the melt period. So you can detect that at the end of the summer. And these are averages over 10 years, over a season. The red is the first 10 years of satellite data, the blue is the next one, next 10 years, and the gold is the following 10 years. And as you see, progressively, the minimum goes down by a bigger and bigger margin. And in fact, if you look at the recent years individually, this is the minimum for 2007 when people observed this dramatic change, and it was even more dramatic in 2012, which is shown by the bold line over here. So this is something familiar to gather already, but the thing is, people keep asking what will happen to the Arctic ice, and we feel that it will continue to decline on account of the fact that there's this ice albedo feedback. Claire and I described that in the paper that we published in Physics Today. You get more and more solar energy as the ice retreats, and in the process then you accelerate the melting of sea ice. The trends are quantified over here. This is for the annual, this is for perennial ice, and actually we are able to get multi-year ice from passive microwave and demonstrate that the trend for multi-year ice is even more stiff than that of perennial ice. The Aqua AMSR-E was launched, and we felt that there's a need to validate the AMSR data. So we had some campaigns in the Arctic, one in 2003. Bob Cahalan was involved in that, and another one in 2004. And we actually managed to get to the ice pack. We were happy, we got there. But then the pilot saw that the red light was blinking, and he said, we lost one engine. And he then further commented that we have 3 engines left. Let's finish the job, since we only need 2 engines to get back. So he he said he started going through our transect, but then another light was blinking. That means we are left with only 2. So we all got nervous.
Fortunately, one on each side.
Yeah. And the pilot decided to go down where it's warmer, and then before we know it, it came back. But it's amazing, you know, nobody panicked. And in fact, during the process, Bob Cahalan was there, and he was just eating pizza. So we got some results in 2004 when we went there again. There was another problem with P3, which this time was actually an AB P3, because the NASA P3 was then out of commission. But we get some useful data, and this is PSR data, which is a simulator for AMSR-E, and we are able to demonstrate that we are consistent with Moody's after we have done applied our algorithm. One of the things that actually was a big surprise and was the fact that the trend in the Antarctic sea ice extent and area is positive as opposed to negative, which is what we observe in the Arctic. And if you look at surface temperature trend, there are also a lot of areas where it's cooling. So there was a book that was published by Michael Crichton. Claire also published an article indicating the positive trend of sea ice and the fact that you have a longer ice season. And he took advantage of these publications, including mine, and used it as one of his bases for claiming that there's actually no climate change. And he said there's a state of fear created by climate scientists who then just wants to get more and more funding from the government. And it's a book that's supposed to be a fiction, but used by some congressmen to justify that we should not put more funding for climate change. And actually, Michael Crichton became a guest of the White House. But what happened is that he forgot that, or he intentionally decided not to include what was happening in the Arctic region, where there's really a big change in temperature and the ice cover is declining very rapidly. We have looked for insight for that change, and the hypothesis now is that we're getting the most increase in ice cover in the Ross Sea. So the origin of the increase in ice cover is actually due to production of ice in the Ross Sea. And we look at the polynya formation. The coastal polynyas are actually the ice factories in the Antarctic. And in fact, there's a study that was done by Jay Arnold and myself that indicates that a large fraction of the ice cover actually come from coastal polynyas. So what we observe is that the size of the coastal polynyas have been increasing over the years. And if you calculate ice production, you get a trend that looks like that. And to verify that, we also look at the drift of sea ice that has been increasing in velocity. So you have more ice coming out of the region, and you get a trend that looks like that. And the trends are compatible. We get something like 20 cubic kilometers per year as an increase. The theory is further supported by the fact that they've done some modeling studies with and without the ozone hole. And with the ozone hole, there's a deepening in the lows in West Antarctica, primarily near the Amundsen Sea. And that creates the stronger winds in the region. So with stronger winds, you then create more polynyas and more ice production. Also, if you're looking at a longer time series, the only data that's available for free satellite are the Welling data and the Macintosh data. And they're summarized over here as the black line. And the average from satellite data is the dark green, indicating that the black line is actually north of the black, of the green. So what this says is that the ice was more extensive in the 1940s and 1950s than the present. There was also an article by Delamere who claims that phenomena. I think you've seen this. There's a poster like this around the hallway, so I'm not going to discuss it, indicating that if you look at a longer time period, there's also a general warming in Antarctica. So going back to the Arctic, I had the experience to do analysis of both NDVI, temperature, and sea ice concentration, their correlation. And there was interest in what's going on over the permafrost area. And just by looking at NDVI, we found out that there's a positive trend, meaning greening of the Arctic. And it's highly correlated with summer warmth index and sea ice concentration. I was invited to go to Hadley to give talks about sea ice and surface temperature. And I encountered this graph on drought, which is actually implication that the drought has increased from about 15% in the 1950s or 1980s, and then it has increased to something like 25. And their projection is actually that the drought area can increase up to 50%. So I started thinking about the Philippines, which is a primarily agricultural area, and decided that maybe it's time for me to do some educational outreach. In the Philippines, they even carve mountains to create these rice terraces so they can plant rice. And this is the livelihood of people. I happen to be a member of a Philippine American Academy, and we actually had our founding symposium in Manila, invited Edward Teller, who is the father of atomic bomb, as our keynote speaker at the time. The key problem at the time was energy. And so we thought of trying to see if we can start building nuclear reactors for energy source. With that connection, we've also been host to the then President Gloria Macapagal. So I managed to find some connections where I could express what I think can be done in the Philippines in terms of drought studies. We studied some NDVI and indicated that there's 1 year when you can see the NDVI to drastically go down and be able to identify locations for drought. And this was highly correlated with temperature and rainfall, because when there was low NDVI, there was also no rainfall and the temperature was very high. So I thought that was very promising. I showed it there and they were encouraged. They wanted me to give lectures on remote sensing. They organized a national remote sensing symposium. I was one of the key lecturers. They were able to invite representatives from universities all over the Philippines. So I thought I was doing something good. We even did some validation to ensure that our interpretation of satellite data is correct. I also did some, organized some workshop on climate change in the Philippines. We invited some experts from the US with Filipino background and joined with the experts in the Philippines. And the workshop was so successful, we decided to write a book about it, and it may be coming this year. And in appreciation for some of my work, actually, I've been invited to Congress, and I've interacted with some senators who wanted to know more on what the Philippines can do to do mitigation and adaptation. In the meantime, I was nominated to be a lead author for the next IPCC. That was way back, I think, in 2009. I accepted the invitation to be nominated, thinking that I wouldn't get it, because there are normally about 3,000 applicants for the position, and they only can take 250 people. But I was surprised in the end that they took me in, and they wanted me to be a lead author of one of the chapters. So that became one of my key projects here at Goddard as well. This is the strategy. I'm not going to read it because of time. But this is the involvement that was required for IPCC to serve as coordinating lead author of the chapter on the Cryosphere. I attended a CS workshop at Delhi, India, because being in the Cryosphere, one of the key factors that affects sea level is the melting of ice sheets and glaciers. So we came up with a zeroth order draft, presented it in Kunming, China, and after that we got some reviews, 100 comments, and after the zeroth order draft, we come up with the first order draft in response to the comment and some enhancement. This is actually the first draft that has the science in it, because the zeroth order draft was just an expanded outline. We got more than 1,000 comments from the first order draft, so that was a lot of work. We then addressed that and submitted the second order draft in Marrakech, Morocco, and after that there was actually 2,000 comments, so that was even more work. So finally we had a draft that we submitted at Harvard, Australia. It was copy edited. We addressed the comments, and we also come up with a summary for policymakers. And that summary was actually the primary object for the Stockholm meeting. These are some of the results that we got. That's the Cryosphere. This is the sea ice cover and the long term, and as you see, it's basically flat until the satellite era, when it started to going down drastically. And these are the contribution to sea level from the various components, from the glaciers, from the Greenland ice sheet, from Antarctica, and this is basically what we did for the Cryosphere, and demonstrated that all the components of the Cryosphere have trends that are in concert towards global warming. So some of the key results from the IPCC report is that warming in the climate is unequivocal. That was said again already in 2007 report, but we have further a lot more data and a lot more accurate modeling to support that, and that the human influence of climate is evident in most regions of the world, globe. So there were modeling that was done to project for the future, and this time we use CMIPS 5, which is the most current modeling system. They look at scenarios from basically no change in the trend in carbon dioxide and greenhouse gases, which is RCP 8.5, to curtailing the greenhouse gases to the present time and make it constant. So to make it constant, the net result is to make the temperature to be flat after a while, but with the current trend continued, you get the temperature to go up substantially. And with the sea ice, sometime it can flatten out and not lose all the multi-year ice, whereas if we continue as usual, then you lose the ice somewhere in the middle of this century. There's also modeling results for acidification. So that's the system in Stockholm. During the plenary, we have Pachori, who is the chief of the IPCC project, and we have 3 reports. WG1 is on the physics of climate change, co-headed by Thomas Tucker and young Dr. Yang. And actually, the government representatives are seated in front with this coordinating lead authors sitting on the side to respond to questions. And sometimes when our chapters are being discussed, we'll be asked to go to the podium. So these are the bars that indicates our progress, and there were lots of questions. So it got to the point where there was very little time to do a lot more of the work. And we are supposed to be done Thursday afternoon. And with that kind of chart, we decided to work until 2 o'clock in the morning on Wednesday. And on Thursday, it took until 5 o'clock in the morning on Friday before it was completed. So the announcement for the report was made at 10 o'clock. We just went home to have a shower and go back for the announcement after that. So what's beyond the horizon? What should we do to combat climate change? Should we do geoengineering? You know, this is the sunset at Stockholm, and the sunsets would even be more beautiful if we put more aerosol in the atmosphere and do some cooling. But I hope we don't go this way, because it would be like asking, taking a medicine without knowing what the side effects are. And then what should we do about the future generation? I finished my book on polar oceans from space, and I gave my daughter a copy, and all of a sudden I get a picture like this. My granddaughter already trying to read climate change. So looking back, I think the jeep accident I had when I was young was unfortunate, but made me change my career goal, which I think was for the better. I'm more than ever convinced that the advice of the Maniac reporter made a difference, because it made me pursue a difficult research project that I would not have done, and some people would have abandoned as well. So thank you for your interest.
So one or few comments?
You made a transition, as you did, from particle physics to earth science. I'm wondering if you reflected back and you feel that that early work in that area helped you in what you do now, or is it sort of completely different?
Yes, most definitely, because the physics is the same, you know, especially when I was doing some radiative transport studies. So all the equations are primarily the same. But when you do dynamics, it's mainly Newtonian mechanics. So in particle physics, it's normally field theory, and you do relativistic calculations using special relativity. So it's a little different, but I think, in fact, it helps somewhat the fact that when I was doing particle physics, I was analyzing a lot of data, like bubble chamber data and spark chamber data. And when I got to earth science, that also involves analysis of humongous amount of data. So there was the convenience of having had that other background as well.
Okay, last one.
So how much does those floating ice, those icebergs, contribute to the total ice? And what the changes have you seen in their population distribution? Means the ice breaking off from the ice shelf. And you have these icebergs.
Are you talking about glacier ice or?
No, I mean the icebergs, floating on the ocean, which called the Titanic.
Yeah. Yeah, the icebergs contribute to sea level rise. At the moment, there's not really a large fraction of them. We have 9 million square kilometers, 90 million, almost 90 million square kilometers of ice in winter in the Arctic, for example. If you think about the icebergs that are calved into the ocean, that's a very small fraction.
Okay, so with that, let's thank him one more time.